Yes. As always, we have land acknowledgement. We acknowledge the land of Omni Reunius Network head office, which is located on York University. And York University recognizes that many indigenous nations have long-standing relationship with the territories upon which York University campus are located that precede the establishment of York University. York University acknowledges its presence on the traditional territory of many indigenous nations. The area known as the Toronto has been caretaken by Anishinaabe nations, the Hudotans, Confederacy, and Huron-Wendat. It is now home to many First Nations, Inuit, and Métis communities. We acknowledge the current treaty holders, the Mississauga of Credit Nations. This territory is subject of the Dish with one school grant of Bill Conway, an agreement to peacefully share and care for the great region. And what we can say about super spreader seminars, the Omni Reunion Super Spreader Seminars, which stands for SSSS, welcomes faculty members, Omni Reunions affiliates, and highly qualified persons, including postdoctoral researchers and graduate students, to showcase their research, promote their ideas, share their research experience, and establish connection among various branches of the network. It's a platform to spread scientific knowledge about the One Health research framework and research progress of over 30 unreunious HQPs within the network scientific research community. This seminar facilitates knowledge exchange within unreunious, the emerging infectious disease modeling, the IDM network, and collaborating scientific community. Today, our speaker is Nixon Gulova. Thank you, Nixon, for accepting our invitation to talk to her today. Nixon is a master's student at York University under supervision of Professor Wildegirima Asafa Wildegirima. He's currently pursuing a double master degree in mathematics for real-world application awarded by Intermath Consortium through an international double master degree program involving the University of Lapua, Italy, and York University. So he has a joint program between Italy and York. And his research has been focused on integrated deep learning with mathematical modeling to enhance the accuracy of epidemic prediction. Especially his thesis explored the use of this important neural network to model the spread of infectious disease. His research interests include epidemic modeling, dynamical system, numerical methods, and application of AI in solving complex public health challenges. Nixon received his bachelor in education, majoring in mathematics and minoring in chemistry. Oh, he has a combination of the stocks. From Macquarie University, Uganda. Following this, he passed a Master of Science in Mathematical Engineering at the University of Italy, Lacuna, Italy, and currently he's furthering his studies in applied mathematics here at York University, where he's applying his principles to real-world challenges through his thesis research. Thank you, Nixon, that we have him here. And he's going to talk about the mathematics of deep neural network with application in predicting the spread of infectious disease through disease-informed neural networks. Okay, so we are going to listen to your talk and to hear about the details by your slides. Thank you, Nixon. You can present your slides here. Thank you. Sure, let me just... Okay, Nixon, you are.
All right. Thank you so much. Thank you, everyone. Those who have attended in person and those who are on Zoom. I appreciate everyone. So I'll present the mathematics of deep neural networks with application in predicting the spread of infectious diseases through disease-informed neural networks, or we shall call them the DINs. Yes, I'll start right away. With the introduction, literature review, methodology, results discussion, conclusion, feature work, and then acknowledgements. So, as we know, AI is a powerful thing right now. Deep learning, we've now seen some advancements, and deep learning is like a subset of machine learning, and machine learning is like a subset of AI. So AI is a big thing. But deep learning, we've seen some breakthrough as a powerful AI tool. Uh, Following the image recognition and natural language processing, it has also been applied to the healthcare. I would say notable breakthroughs in the development of different architectures like the CNNs or the convolutional neural networks. And the
have it. Share your slides. Let me. Okay, let me share this one. Okay, let's can you see these slides right now?
Sorry, no, we can't see them online. We can just see the downloads window on the computer.
Okay, let's be making co-host for that. Okay, share and wait. How about right now?
Yep, yeah, I can see a slide now. Thanks.
Thank you.
sharing the task.
Yes.
Is slides.
So yes.
Okay, close now. See. Is everyone able to see the slides?
Yeah, we can see them. Thanks.
All right, thank you.
Thank you.
Yes, so I've been talking about the introduction. Like I've said, there is a breakthrough in the AI, and we've seen deep learning as a powerful AI technology that has come up right now. And I was still talking about different architectures as like convolutional neural networks and recurrent neural networks. We shall talk about this one like later on. So why is deep learning important, or why is it applicable like, to disease modeling? So it's important in predicting the spread of diseases and controlling the disease spread. So, and we've seen that the traditional models like the SIR and the invariant SEIR have limitations. So yes, so that's why the deep learning models are now important for this case. Okay. So we also need to integrate deep learning to enhance the model accuracy and predictability. So we shall talk about the definition and the purpose of the beams, and then we combine deep learning with the theoretical models, and then we also look at how their performance, how deep learning is performing in predicting the disease spread. So the recent COVID-19 pandemic underscored the need for advanced modeling techniques, and here we are to discover the beams and apply it to different other diseases. So for our case, we shall not talk about the COVID-19, and we shall talk about the avian influenza. So the goal is to improve the implementation of classical models with deep learning for better disease spread modeling. So where did everything start from? Deep learning, or AI in general, started in 1940s, and specifically in 1943 by the work of Warren and Pitts, who came up with this brilliant idea to come up with something that can predict or mimic or something that resembles the human brain. So they introduced what we call the neural networks in 1943. And Some other person called Seppo in 1970 came up with the backpropagation, which was a method that was used to improve the performance of the neural networks. And by then, no one took interest, or no one really had interest in AI or deep learning. So not until the 2010s, but specifically in 2012, there was a competition about the ImageNet competition using the CNNs, or the convolutional neural networks, that brought up their attention to the world to understand, okay, these algorithms or these deep learning models are really, really good. So as of today, recent advancements have been seen in transformers and generative models. And transformers, these are used in the natural language processing, like ChatGPT and Cloud and so on. So applying these into the epidemiology,
I already added the application of myself and Professor Wu.
We've seen different authors trying to apply all these deep learning models to other infectious diseases like COVID-19. So a lot of research has been done. And then we've seen the development of the disease-informed neural networks by one researcher. But there are challenges and issues in this case, like data quality and availability. And there is need for model interpretability and transparency, also using the real data integration, and also personalized medicine and policy planning. So we shall talk about, this research has two parts. One is to talk about the mathematics of deep neural networks, and then we see how we can apply it to predict the spread of avian influenza. So we shall first of all introduce what a neuron is, like mathematically. So a neuron is just a function. Mathematically, it's a function comprised of weight, bias, activation. So when you have inputs, weights, we sum everything, we add the bias, and we activate, we get what we call a neuron. In this case, we mean an artificial neuron. So it's trying to do the same role as a biological neuron, because we have dendrites and so on. So activation is also done almost in the same way to mimic the biological brain. And basically, this is the structure. Basically, this is the structure of the artificial neuron. That we have weights, we have inputs, we have weights. When we sum everything and add the bias, activate, we get the function F, which is called an artificial neuron. And from the neuron, we get a network of neurons. So when you get a network of neurons, we get what we call a neural network. And formally, this is the definition of the neural network. But the most important thing is the affine linear transformation, as we can see here, the TLX, which is the sum of the weight matrix together with the input vector plus the bias vector. So in this case, when we get the composition of these affine linear functions together with the nonlinear activation function, we get what we call a deep neural network. So briefly, that's what we call a deep neural network. It's just a composition of these affine linear functions with the nonlinear activation functions. And we say that it's a deep neural network of depth L. So deep in such a way that if we have more than one hidden layer, then we call it a deep neural network. So like in this structure, we have a deep neural network. We have the real hidden layers, we have the output, we have the input. So this is a deep neural network, which is just a function phi from R10 to R2 with depth 4. Depth 4 meaning that we have 4 layers. And when you look at the input layer, in this input layer, they're just nodes. There is no computation done in these nodes you see. They're all green, but the computation is done right from the hidden layer, where we see the computation I'm talking about is the computation we've seen in a neuron, where we have inputs, some being summed with the weights, add bias, and activate. So this is where the computation is done. So we have 4 layers in this case. So we have depth of 4. So there are various activation functions, but we should, these are mostly the common activation functions. But in this case, the common would depend on the importance of different activation functions. So the rel is the most common activation function because it helps us with vanishing gradient problem. So it solves this issue. And then the hyperbolic tan, this helps us in zero centering like data. So to fit actually the biology in this scenario, in case you're talking about public health. So we also have different architectures like the convolutional neural networks or the CNNs. They are suitable for grid-like data, like in images. And yeah, we've seen these architectures being applied like a lot. For example, this architecture is also applied in AlphaFold 3, but previously it was AlphaFold 2. And this AlphaFold 2 is used, it's a deep learning algorithm or a model that predicts the protein structure. So this is also used in DNA, and this kind of architecture is being used. So we also have the recurrent neural networks, the RNNs. They use sequential data like time series. And in here, we also have, in these recurrent neural networks, we also get what we call the long short-term memory, the one that we talked about, like just as a breakthrough. So for our case, we're using the feed-forward neural network, which is just the simplest form of neural network. It's just like a basic architecture in our case. So it's just where the information flows in just one direction. It just follows a forward format. So in our training and optimization, we use what we call the loss function. And in the loss function, we require some errors, which is the mean squared error and the cross entropy loss. But this all depends on the selection of these, depends on the kind of data you're dealing with. For regression data, it's advisable to use the mean squared error, and for classification data, it's advisable to use the cross entropy loss. So the other one is the backpropagation and gradient descent. So backpropagation is just a method that calculates the gradient. It calculates the gradient of the loss function with respect to the weights. And in this case, the weights are also called the parameters. So this is very important because we use this kind of method in improving our optimization. So this is just a method that is used for optimization, like in the gradient descent or stochastic gradient descent. These algorithms require to calculate the backpropagation. So we also have a theorem called the universal approximation theorem. This is really very important in the research direction of expressivity, because expressivity, we are trying to look at the performance of our model. So this was proved by George. And what does it state? So mathematically, it states like the way you see it in the slides, but basically it's saying that if we have like any continuous function can actually be approximated as long as we have sufficient neurons. So it can be approximated to its arbitrary precision. So it doesn't really matter as long as we have at least one hidden layer. So it's okay, and we have our nonlinear activation functions. We can still approximate any continuous function, but there are some limitations that it should be on a compact domain. So this is very important as well, but it does not really tell us how to do it, but it's just telling us that if you have a shallow neural network, you can still approximate continuous functions. So we shall now go in the prediction part where we introduce the avian influenza. But before that, so now we're talking about the applicability of our disease-informed neural network. But before that, we have different classical models. We have the SIR and the SAIR. but we're interested in the extension of these models, these traditional models. And this is the SISIR, which is for avian influenza. And this is the model equation. Basically, avian influenza is bird flu that involves the bird population as well as the human population. So these are the parameters, definition of the parameters and the variables. We have just avian population and we have the human population together with 12 of these parameters. So our disease-informed neural network is going to be able to predict predict the spread of diseases, but the DIN will first of all predict the parameter, or it will estimate the parameters. So we shall have the values, it will estimate the parameter values, and then it will use them to predict the spread of diseases. And we used a 12-layer neural network with a ReLU activation function. The input is time, the output is state variables. And the loss function involves the data loss and the physics loss. This is the most important part of our research, that our loss now requires us to have the data loss and the physics loss. And the training was done using an optimizer, which is the Adam optimizer with the learning rate scheduler with 50,000 epochs. The epochs are the iterations, but these were important for us to have convergence. So as I'll say, the most important part is the loss. So that in the loss, we have what we call the data loss and the physics loss. And the DIN follows what we call a physics-informed approach, or the physics-informed neural networks, which are called the PINs. So in case you know something about them, the PINs require us to say, okay, if we have a model, for our case, okay, I'll talk about the structure here. So the disease-informed neural network architecture is here. And when you look at from the time to the output, from the time input to the output, this is basically the standard neural network architecture. But we have an extension that we extend it further, that instead of just estimating the output parameters, in this case, we have the state variables, SAT, IAT, SHT, IHT, RHT. These are the state variables. So it's able to predict the population, the susceptible population of the avian and the human, and also the recovered humans. But the most important thing about the DIN is that it goes ahead and it also considers the physical dynamics, in this case, the biological dynamics. So it goes ahead and gets the derivatives. So it computes the derivatives of these state variables using automatic differentiation. But this automatic differentiation is used by the AI frames, like PyTorch or TensorFlow. And then we also use this to estimate the parameters. So this is the most important part. But from here to there, it's the standard neural network architecture, but it goes ahead and extends. So it will require two losses. Like we have the data loss, that is from here to this side, and then there's physics loss to be able to see that, okay, the system is satisfied, or the model is following the dynamics of the disease dynamics. So this is the other part. Okay. So as per our results, the dynamics of our avian influenza model under different scenarios were conducted, and we considered some simulations that were done by some author, and then we tried to see, okay, these were varying depending on the parameter beta A, which is the transmission rate for avian to avian or the bird. So in this, it gave us two scenarios where we have either disease persisting or becoming extinct. So yeah, this is how it looks like. This simulation was depending on the fact that when this parameter beta A gives us two scenarios: the disease extinction and disease persistence. Now, we would like our disease-informed neural network of the DIM to be able to predict this kind of disease spread for alien. So we trained our DIM, and we also used it to predict, to estimate the parameters. So as I said, we trained it for 50,000 epochs to have convergence with that optimizer and learning rate scheduler. So the training process took approximately 28 minutes of war time. But this is after optimizing like through the code. But at first it used to take 5 hours or 4 hours until when it was optimized up to 28 minutes. But I'm pretty sure it could still be optimized further, depending on the resources. But for our case, we used a supercomputer, but if you have like a GPU, it can also be, this 28 minutes can be turned into like 3 minutes for 3 seconds if you have like a GPU. Okay. This is how results were. Like the parameters were estimated really, really well, but it all depended on the learning rate, which was 1x for -4, and the time points of 1,000. And the selection of these depended on using different time points to see what results we get, and also a search range. So when you look at the table, we have the search range. So but all the search range, we are trying to give it, so it's trying to target, the target value is 0.005, but we are saying, okay, make sure you get this value, you approximate this value, but in this search range. So we gave it a search range of 1000%. So it was able to predict it to a value 0.004777. So with a 4.46% error. So this was really, really good. And as for all the other parameters, it was able to do a good job. And despite the search range, because this is a very big search range, but when we try to make the search range closer, like if you give it a search range of 0, it will predict the exact value the way it is. So we try to get some bigger search range. And also the other hyperparameter tuning also became important, like when it came to the time points. When we used 10,000 time points, it took more than 28 minutes. So that's when actually it took like 5 hours or even more than that. So time points was very important, and the learning rate, but most importantly, the time points. So to reduce the time points, the time for convergency, it was important to reduce the time points. And this is how, as we can look at this, during the training, our team was able to be trained really well and so fast. And you see, as we say, we used 50,000 epochs, but even at 40,000, it was already converging. So it was already good. So you can see that there is a drop in the loss. This was very important for our test. So the evaluation of the DIM, the DIM's ability to predict the disease dynamic standard various scenarios, we can say it was a success, and it was able to capture the disease extinction and persistence, as you can look in the graph. So we have the dotted, the solid lines and the dashed lines. So the dashed lines, this is the predicted values, and then or predicted data, and the solid ones are the true data. So it was able to capture this. So when you look at the fitting really was really perfect. Like, so it means that our team was able to predict this disease spread despite this kind of scenarios that were in the model. So this was really very important for our case. And the performance across beta A values, we found some challenges, especially with estimating the IA, or the infections of the avian. So the performance, but otherwise the performance was really good if you look at the relative mean square error loss. So yes, we can say, yeah, our team did a good job, like was successful in having some model like the DIM to be able to predict the avian influenza, so we can call it a success. Though there are limitations like sensitivity to hyperparameters, we should be careful in selecting our hyperparameters, and the computational costs also, and also the need for us to use this and apply it to the real world application. For our case, we use synthetic data, but we're pretty sure that, and I think we're working on this, or if anyone wants to use this kind of model, you can also be able to use it for the real world data, as long as data is available. And you shouldn't worry about if the data is limited. For our case, the DIM will be able to solve that issue because it follows the physics-informed approach. Also, the potential to inform the public health policies and interventions. This is very important for our DIM. Yes, we can, as I said, still we're successful that it was able to predict the disease spread for avian influenza, and the potential program for future research and real world application. Still talk about this, and promising result with room for further refinement and the need for continued exploration and validation with real data. I've also talked about this as future work. This will be very important also to apply it in other diseases like monkeypox or meningitis and so many. It has been done for COVID-19, so we can still use it for other diseases, and also use it for other architectures like the LSTM or the long short-term memory. Because for our case, we use the disease informed neural network, but someone else can use a different architecture, because our architecture follows the feed-forward neural network, but you can also use it for the long short term. But this is all future work that can be done. I really thank you so much. I thank Professor Sekwa for supervising me, and Professor Waiping for all the support, York University, University of L'Aquila, and the Department of Math and Science. Thank you so much. I really appreciate it.
Thank you, Asif. We really enjoyed it. Thank you all. Thank you. Let's have. Let's have, see what we have here. Let's make the call. Thanks, Professor. This work was done under the supervision of Professor Asefa, who is the leading of the Omnia Reunions. We really thank Professor Asefa and Professor Zhu as the main director. Thank you both. Let me just make the co-host. And
can I raise my hand?
Yeah. Let's have it.
Yeah, just comment, no question, because I have asked him a lot of questions during his MSc thesis defense. Actually, I'll begin that the thesis of Nixon is already completed. He has successfully defended his MA thesis, and he got an outstanding grade. And I just want to also thank for Nixon for the great work. He was able to do much of this work by himself, and the presentation was outstanding today. I also want to acknowledge and thank Professor Waiping Zhu for the directing the Real Math program, which is a collaboration between York University and L'Aquila University in Italy, and also for trusting me to work with him and with Nixon. And thank you very much, Professor Zhu. Back to you, Sanez. Also, Sanez, that's interesting coordination of these SSS Zoom meetings, and the introduction was excellent. Thank you for the.
Thank you so much. Thank you. Yeah. Professor Zhu is the main director of this event, so I really appreciate all of you for attending here. Professor Zhu, is there any talk or any comments, any suggestions you're just learning here you want to mention? Okay. Otherwise, we can go through the questions. Is there any questions from Nixon Hawk. You can put it down, write it down in the chat, or you can share and raise your hand for any questions, any comments, suggestion.
Yes, I have.
Okay.
Nixon, did you have any limitations? Any limitations? Any limitations? Yeah, with the home market. Yeah, sure. So no one has asked if there were any limitations, like as per the dean. Yes, I've talked about some of them here. Like the limitation one was computation time, like instead of 28 minutes, because at first, there was some kind of hyperparameter tuning. So when the time points were really big, like the model was taking long. So the code was taking like 5 hours to run. So until when I made it up to 1,000, I was like, okay, so now it takes 28 minutes. And this is maybe the minimum I could go. But if I had like different resources like GPUs, I could even go faster than that, because GPU is able to
go further.
Right.
You probably go a 7
Yes, it can even take 10 seconds or so.
Yeah. Okay.
Right.
Sounds very interesting. Very interesting. Congratulations on your hard work, and I only expect and hope that you will do better and go further, because I know this is maybe just the groundbreaking of your model, and in time to come it will just so,
thank you so much. I really appreciate it.
And we have any question what real world true data were these prediction compared to, and where did the input values from NN come from? Yes, this was any questions that we have in the chat. What real data were these prediction compared to, or any?
Okay, no, so as I say, so the data we use is synthetic data. So as part of the future work, we're looking forward to use real data, because I never got time to get the real data to use it for our team. So this is one of the future work that is going to be done, or maybe anyone can do it. So I did not compare it with the real data, but it can be done with real data. And where did I use the input values? So I use, first of all, the DIN follows the physics-informed approach, so it takes time as the input. So in the data, in the synthetic data, there is time. There is also the number of susceptibles, infected, like all other compartments, but with respect to time. So it takes in time as the input value, and then it outputs the state variables, S of t, I of t, and so on. So it took in time as the output, and then it estimated the state variables, and then it went ahead to go further and get the derivatives using automatic differentiation. And then that's how it estimated the results, like the parameter estimation. But the data was also seen in the data loss. So data was also seen in the data loss. So that's the way it took in the values, the input values. So it took in time, and the rest of the data was used in the data loss, in computing data loss. Yep.
Okay, thank you. We have Emmanuel, and he said that was a great work, and thank you, Emmanuel. And Samuel, great work, brother. You are a great inspiration. So that is all great.
Yeah, thank you so much. Most of these students are actually Lapida students, like from Italy. They are in Italy, yes.
Yeah,
thank you so much.
It's really promising and interesting that we have some students at NU from Italy that joint work between these two universities. Thank you. I by myself have a minor question.
Yes.
What made you to make 12 layers? In a general form, I have some of my friends working with different kind of GNN, and they have 10 network layers. I mean, what makes you to choose 12 or how to make it efficient?
So just like the same as the hyperparameter tuning. So the 12 layers was selected because it was like a choice, but also it was able to give me the correct results. Because I tried it out with like when you try to read my research, like in master thesis, I explained all that like in the thesis, but I used the 8 layers, I used the 10 layers, I used the 12 layers, I used the 14 layers, and I realized that, okay, when I have 14 layers and 12 layers, mostly giving me the same results. But the 10, 8 were giving me results that were not that accurate compared to the 12. So the selection is also basing on like you try out something and see if it works and to improve the performance of this team.
Thank you.
Yes.
And how can we, how the properties of the disease we're working on can be contributed to have the most output, to have the output that, I mean, is it dependent on the learning rate or something? How to make it specific for any disease? No, this is the general form. Your linear architecture is for SI. Yeah, I mean, how to make it specific for, I don't know, fat liver, specific for, monkeypox, as you mentioned.
Yes, actually it doesn't change that much. Like, because what you have to do is to change the structure of the model. Like the model is going to completely change, but the rest of the thing is going to be the same. How you're computing the automatic differentiation is all going to be the same, but it's just changing the model. Because in this case, we have like, there were 5, like, equations in the model. But if you have, let's say, another model that has, let's say, COVID or any other, maybe Mpox, so it's going to increase depending on the complexity of the model. So also the time is going to be different. So this was for avian, but for COVID-19, depending on how complex the model is. Let's say if the model has like 12 equations, then this is also going to be complex. So it's going to take maybe much time. It means you need to do more computation. Maybe you need also to get more layers. So, but for this case, it took 12. So maybe for that specific model, it can take more than that. But we should also know that the more we extend the layers, having more layers, we get good performance. Like the model performs well than having many neurons in a layer. There is a difference. So we can have many neurons because you realize I also use 64 neurons in each layer. But I could also use maybe 100 neurons. But I realized, okay, using 60 neurons is just sufficient enough, but I also use some other neurons. So when I have 64 neurons in every layer and I have 12 layers, it was sufficient. But I also tried out others, like how about when I have this, when I have this. So I just decided to go with that, but it's not the only way, it's not the only model. So it's just flexible to take on any format. Yeah.
Thank you so much.
But I guess it would probably be easier if you had more equipment.
Yes.
To do that, and it wouldn't take that long, you might be able to.
Right, exactly. So if you have like GPUs, like you don't have to worry that much.
Yeah.
It will take less time.
Yeah.
But for our case, we had to find ways of optimizing because of the resources we have. So resources is one of the most things that is really bothering AI. So that's why I had to keep optimizing. Yeah.
Thank you, Nixon.
All right. Sorry?
Do you intend to improve on it or?
Yes, I intend to improve on it, especially if I have support, support and everything. I intend to improve on it, yes.
It sounds promising.
Right, yeah.
Thank you, Nixon. Thank you, Nolan. Is there any comment, suggestion?
There's a question there.
Yes. How was the model assessed for overfitting?
Yes, that's a great question actually. But for this case, I did not actually because I did not really talk about the overfitting and all that because in the code I managed to solve this. The code is going to be published online, like when this research is published online. So, but there is what you call the self epsilon that I used in making sure that overfitting, like to solve this problem of overfitting. And there are certain things that I didn't include in this, like the noise. I didn't the data. I didn't put like noise to see how the model is able to handle the noise and all that. So this is one of the things that I can consider in the future work. But overfitting was done like just a little bit, not that entirely, and it was done in that solve epsilon that was used in the coding part. Yeah, but it was not really fully covered or assessed.
Thank you.
So I'm guessing this is something that you could probably consider as you try to improve the current system.
Yes, yes.
So, is there any more question or comment, suggestion? Okay. I think we have covered all questions. Thank you all for joining. Thank you, Professor Junior. Thank you, Professor Stefano de Grima. Thank you, Nixon, for the talk we had here. Thank you all. We are going to have, thank you, we are going to have this recurring meeting in the last week of each month. So the next one will be in the last week of November. We will be pleased to meet you all again there. Thank you. We can stop the sharing right now.
Thank you all. Thank you,
Thank you.
everyone.
Bye-bye.
Thank you.
Have a lovely day.
Yeah. Is there any final comments you want to make,
No.
Professor?
I don't know if Professor Wiping want to say some final comments.
Yes.
No, thank you. It's a great event. So let's stop here.
Excellent.
Thank you, Professor Zhu.
Thank you.
Thank you all.
Okay.
That's the big